Okay, we are now live. Uh, Welcome everybody to our fourth math talk of the semester, our final one. And this is quite exciting. I don't think we've had this much math talks in a semester before, but it's excruciating circumstances, or I don't, that wasn't the right word for that. But we are here with Dr. Todd Mullen, who's a postdoc in our department, working under Dr. Duffy. He's main field. Well, he got his PhD from Dalhousie in March, making him one of the first class of PhDs done over Zoom, I guess. Um, his main topics of study are combinatorics. Well, he did his honors and his PhD in graph theory and his master's in game theory. He told me. Hope that was correct, but. Now we're here with his talk, ChipFiring and Polyominoes, and I will hand it over to Todd uh, for the rest of the hour. So welcome.
Okay, thank you. So I'm going to see if I can get this screen sharing to work.
Okay.
Okay, can you see that?
It's just loading. Hopefully. There we go. And I'll turn my camera off, so take it away.
Okay, great. Okay, the name of this talk is ChipFiring and Polyominoes. My name is Todd Mullen, and this is joint work with my PhD supervisors, Richard Nowakowski from Dalhousie and Dr. Danielle Cox from Mount St. Vincent. And this is November 25th, 2020. Now, I've got a few different windows open here I'm going to be trying to bounce between. This is all a little new to all of us, I'm sure. So let's go here. Okay, so this field is graph theory, and I want to give us some basics before we dive into the chip firing aspects. So what I have drawn here is what we call a graph, maybe a little different than what some of you are used to knowing as a graph. In the field of graph theory, we just call anything a graph if it is a bunch of vertices, which are these black circles I've drawn, connected in some way by edges, which I've drawn in blue. So it's a very broad field. It's really anything that can make use out of these structures that we call graphs. And in particular, what I like to look at are dynamic problems. Sorry, what was that? Okay. So I like to look at dynamic problems on graphs. So that is ways that you can view graphs as maybe a board for a game or just any model for a map for how things can move around. Some types of problems you think about games of cops and robbers where one character chases another around trying to capture them. You can even think of chess as being a game that is played on a graph as you think about the different movements that pieces can take as following these blue edges from square to square. Today, what we're going to be talking about is chip firing. So I'm going to try scrolling here. So chip firing on graphs was introduced, I think in the 80s, but this is a good paper from 1991 that will give you the introduction by Bjorner, Lovash, and Shore. And what chip firing is, you take a graph. I've drawn a graph here. You can have whatever graph you like. And you assign to each vertex a value, an integer value, representing the number of chips that reside on that vertex. So you can see here we have a vertex with 2, vertex with 1, with 3. Some of them are completely broke. They have no chips. And the rules for chip firing are, at every step, the player, which is me, chooses a vertex that has at least as many chips as it has neighbors. So the word neighbor just means another vertex that you share an edge with. So if you look around, you'll see in this first example, there are 2 vertices that have at least as many chips as they have neighbors. This vertex here has 2 chips and 2 neighbors, and this vertex has 3 chips and only 2 neighbors. And what you do is you choose any one of these vertices to fire. And what firing means is to send one of its chips along each of its edges. So if I choose this vertex here on the left with two chips on it to fire, you can follow this blue line to my second graph that I've created, or it's the same graph, it's just a different configuration of chips. The two that were here have been moved along these edges to their neighbors. And this is a game that you can keep playing potentially infinitely. It's possible that there could be so many chips on this graph initially that you'll never run out of vertices that are primed to fire. But we'll see in this example what happens. If you look around, you'll see that now there is only one vertex that is primed to fire, and it has 3 chips on it. So we'll fire it, following our blue arrow. And now, glancing again quickly, we again only have one. This vertex has 3 chips and 3 neighbors, so we'll fire it. And again, it has lost all 3 of its chips, gone down to 0, and its neighbors have each increased by 1. And now we have again one vertex that is primed to fire. If we continue this game on, it's possible that we eventually reach a situation where no vertices are primed to fire. You'll notice that none of these vertices have at least as many chips as they do neighbors. So that's why I've drawn this arrow looping back to itself. If you were to continue running this game, it would be for naught because nothing's going to happen. So at every future step, you'll just have the same configuration of chips. So that is our broad strokes of what chip firing is. So what I'm going to talk about today is diffusion, which is a variant of chip firing that was created by Dr. Duffy and his co-authors in a paper published in 2018. Here we go, diffusion. And here's where I'm going to try to bounce back and forth a little bit. So my next slide. What is diffusion? Diffusion is a variant of chip firing in which vertices fire simultaneously. In the previous example, we had vertices firing one at a time, and I was choosing which vertex to fire. But in diffusion, every vertex fires at the same time. Now, firing has a slightly different meaning. At each step, each vertex doesn't send a chip to all of its neighbors, but only to each of its poorer neighbors. So we'll look at what this means. Suppose I start with just a simple path, just 5 vertices connected by 4 edges, and I assign stack sizes of 7, 1, 9, and 7. Under the rules of chip firing, I could have chosen either this 7, this 9, or this 7 to fire, and then we would have maybe continued this game for a while. But under the rules of diffusion, I don't get to choose anything. The player doesn't do anything. The game is already defined. Every vertex fires a chip to each of its poorer neighbors. So what that in fact means is these 2 1s here, these 2 1s are not going to fire to anybody poorer than them because there's nobody poorer than them. So they are only going to receive. So in this next step, what has happened is the 1s have each received from their richer neighbors. In this next step, you're going to see that the 3s are still poorer than their neighbors. So we come down to something like this. But just like in chip firing, we found an instance where the firings have stopped. Everything reached 5. We've reached our equilibrium. So if I were to keep playing this game, again, nothing would be accomplished. It's always 5s from there on out. So the first question one might have is, if you're playing diffusion, is it always going to end up this way? Is it always going to reach a perfect stasis where every vertex has the same stack size? So here we have another example. We're still looking at the simple path, but I've assigned different starting values. And as we move along, again, the 2 is richer than its neighbors, so it sends a chip to each of its poorer neighbors. The 4 does as well. Now we get an interesting situation where these 2s are tied, so there isn't actually going to be a chip moving along either of these edges. So in this next step, the 2 and the 1 both fire to the 0. And we continue along. And what you'll notice is 1, 0, 3, 1, 2, this 4th one down, it is actually repeated. It is also the 6th one down. So if we were to continue playing this game, we would get just this flipping back and forth of 1, 0, 3, 1, 2, 0, 2, 1, 3, 1. 1, 0, 3, 1, 2, 0, 2, 1, 3, 1. So this is an example of something that is said to have period 2. Whereas the previous example had period 1. Once you start repeating, there's really just one configuration that repeats over and over and over. In this instance, there are 2 configurations that will flip back and forth for the rest of time, as long as you continue playing the game. Now, I've got an example drawn up here on a complete graph. So a complete graph is a graph where every possible edge exists. So between every 2 vertices, you'll notice that there is an edge between them. And again, I've just assigned some stack sizes here, 4, 3, 2, 0, 0, 1. But now there's so many more edges. So if we look at this 4, it has 5 poorer neighbors. So it's going to go all the way down to -1. So if you'll think back to ChipFiring, a negative value was never actually possible because you would never fire more chips than you had neighbors because you were only primed to fire if you had at least as many chips as you had neighbors. So that's one thing we need to accept from the get-go on diffusion is values will go into the negatives, and that's just something we're going to deal with. So as we see, the 4 is fired and gone down to -1. If you think about the 3, it receives 1 from the 4, but it gives away 4. So it's actually going to go down by 3 down to 0. And you'll notice all the other ones have changed as well. But as we scroll down to our next one, we actually get that we've returned to the initial graph after only 2 steps. So this is an example of a period 2, just like we did before, because this 4, 3, 2, 0, 0, 1 is the same graph we started with, 4, 3, 2, 0, 0, 1. So we've already seen examples of period 1 and period 2. And the important result, the important result from last year in diffusion that was published that really defined where diffusion, the study of diffusion was going to go from there, came from Jason Long and Narayanan. And it says that every single instance of diffusion on any graph, no matter the initial configuration of stack sizes, will always have either period 1 or period 2. This is far from trivial, and I'm not going to go into the proof now, but that is something that is very necessary, and we're going to be referencing over and over as we continue through this talk. Now we're going to talk about prepositions. So you can think, if I start at this position, 4, 3, 2, 0, 0, 1, the game is easily defined for me to figure out what the next position is. I just fire every vertex 1 chip to each of its poorer neighbors. But how could I move backwards? How could I figure out what sort of configuration could have potentially led to this 4, 3, 2, 0, 0, 1? So as I have written here, every position has a preposition. This isn't trivial, but we'll show one way that you can build a preposition. One way to build one is to switch the subtractions with additions. And what I mean by that is, suppose we started with this graph, 2, 5, 0, 3, 1. Now, on the right, we can see where it goes naturally. Without even looking at it, I can say that the 5 is going to go down to 2 because it has 3 poorer neighbors. The 2 is actually going to stay the same. It receives from 1 richer neighbor, but it also gives to a poorer neighbor. So there 2 should be staying the same. 1 should receive from all 3 of its neighbors, going up to 4. 3 should give to both of its neighbors, going down to 1. And 0 should receive from both of its neighbors, going up to 2. That's what you see on the right here, 2, 2, 2, 1, 4. On the left, all you need to do to figure out the preposition is to do every one of those calculations in reverse. So instead of that 5 subtracting 3, I should add 3 to get up to 8. Instead of that 0 adding 2, I should subtract 2 to get down to -2. And you'll notice that this works, because if I were to fire from this graph, I would invariably end up with this 2, 5, 0, 3, 1. So now what we have is that starting from any position, I can follow the rules forward to get the next natural position, or I can actually go backwards. And the fact that I can always go backwards proves that there's infinitely many unique prepositions. So you can go back infinitely far. That is to say, depending on the initial configuration that you choose, there may be many steps before the period becomes apparent. Because, for instance, if we were to go back to this example, at the very beginning when I had 0, 2, 0, 4, 1, it wasn't immediately clear what the period was going to be, how long the period was going to be, or how many steps it was going to be before the period appeared. It was 1, 2, 3 steps until I reached my 1, 0, 3, 1, 2, which was a configuration that would eventually repeat itself. So this infinitely many prepositions argument says that I could have actually started a million steps in the past, and this would have been a much different looking thing. It may have been negative a million chips on the first vertex, positive a million chips on the second vertex, and so on. Take a million steps or so till we get to the period. It can take arbitrarily long, being the point here. So we reach our first open problem. Given an initial configuration, can you determine the period configurations quickly? And the question being, if I just give you an initial configuration, can you determine a quicker way than just running through the process as many times as necessary to reach the period configurations? And this is an open problem. We don't have any way to answer this so far. Okay. So I may have already used the word configuration. A configuration is an assignment of integer values to the vertices of a graph. Remember, from the original ChipFiring, you couldn't have a negative number. It didn't make sense within the context of the game. They would only be positive numbers. They would represent the number of physical chips that you leave on a vertex. But in diffusion, in order for the rules to be consistent, you need to deal with this concept of debt. A vertex can fall into debt, meaning negative integers. So our goal, eventually, is going to be to create an infinite sequence in which the nth term is the number of configurations that exist on Kn for all n. So Kn is a complete graph. Like I showed you before, graph that has all of its edges. So this would be called K6 because it has 6 vertices. So if we go back, what I would be trying to solve for is how many configurations exist on the complete graph with 6 vertices. And then I would want to be able to solve that for any number n. How many configurations exist on the complete graph with 1,000,000 vertices, and so on. That's going to be our goal today. Here's the problem. Every term of that sequence is quite clearly infinity. Every integer is fair game for a configuration. It's assignment of integer values. And there are infinitely many integers. So clearly there are infinitely many configurations on a complete graph, or any graph for that matter. So can we salvage this? Can we make it interesting? We've clearly asked the wrong question. And I've given this talk a few times before. I've tried to fit it into 20 minutes. I've tried to fit it into 40 minutes. We'll see how I can do it, stretching it to an hour. But what I like to do is explain it kind of in the way that I actually did the proofs and I did the work during my doctorate. And this, it works well for undergraduate students because it kind of gives you the process of what it's like to be a graduate student trying to solve a problem. Because before you can solve a problem, you need to find an interesting problem. So here, quite clearly, we did not find an interesting problem because our sequence that we wanted to find, well, it's just all infinities. So we need to ask a better question. So we're going to restrict the list of configurations down to something finite, down to a better question, and then we can start worrying about answers. So adding a constant. So here's the next thing we need to know about diffusion. Let's look at this simple configuration on a graph. I've just assigned 1, 3, 0, and 5 chips. So if you move to the next stage, quite clearly, 1 has received from its neighbor 3, 3 has given to both of its neighbors, 0 has received from both of its neighbors, and 5 has given to its one neighbor. Create 2, 1, 2, 4. Let's look at the example. initial configuration is just what I had up here, except I added 3 to every vertex. So 1 becomes 4, 3 becomes 6, 0 becomes 3, and 5 becomes 8. What you'll notice is as I move to the next step, that the same thing holds on the right. Every vertex is 3 greater than the one above it. 2, 5, 1, 4, 2, 5, 4, 7. Now this is hardly a proof, but what is true and what this is signifying is that every addition of a constant integer to every single vertex does not change the flow of chips. It doesn't change the motion in any way. So if you think about it, when I was considering all the configurations and I wanted it to reach a finite number and I wanted to use combinatorial methods to count them up, it was fraught from the beginning, because even just given a single configuration, this 1, 3, 0, 5, I can add any integer, and there are infinitely many integers, to each one of these vertices and create a new configuration. But my first restriction I'm going to put on myself is say, I'm going to bunch these all into the same equivalence class. I'm going to say, well, if the motion is completely the same for all of the chips, if I add a constant, then I'm going to say that if any 2 configurations represent an addition of a constant to every vertex, then they're in the same equivalence class. I'm not going to count them as unique. So now, instead of counting configurations, I'm actually counting equivalence classes. So that's our first restriction we need to apply to ourselves. But what you'll notice is we still haven't reached a finite number, because there are infinitely many prepositions. So I not only need to get rid of these scalar restrictions, but I also need to just say, I'm only interested in period positions. I'm only interested in counting those configurations that exist in some period, not all those millions and billions and infinite pre-period positions that I just proved can exist. So those are the 2 restrictions off the bat that I need to apply. So that's what we've got written here. Firstly, we observe that since every configuration has a preposition, pre-periods can have any number of configurations. Thus, we will restrict our view only to configurations which exist inside the period. Secondly, it has been shown that every configuration on every graph will yield a configuration sequence with a period of 1 or 2, and that is Long and Narayanan's result. This makes counting much more reasonable, as we know that for each configuration in which we are interested, it shares a period with exactly 0 or 1 other configuration. Since we don't have to think about the possibility of periods of length 10 or 20 or 50, we only have 1 or 2 as the length of the period. It's going to make it much easier to count these period configurations, because as soon as you have one period inside a period, one configuration inside a period, it'll be very easy to find the other one. You don't have to run through it 50 times to see how long the period is. And our final restriction we need to apply has already been mentioned. It has been shown that adding a constant integer value, k, to each stack size does not affect the configuration sequence. So we started with an uninteresting question, but we can put these restrictions on it so that now we actually have a finite number that we're counting. So we go back to our question. How many unique configurations can exist on a complete graph? Well, to answer this question, we must define what we mean by unique. So we will say that 2 configuration sequences are isomorphic, not to be confused with 2 isomorphic graphs, but these are isomorphic configuration sequences. If within the period, because I'm not interested in pre-period positions, the corresponding steps only differ by an addition of some constant to each stack size. So that's me piling all of my restrictions on top of each other until I have a definition that will give me a finite number. So if we go back to the initial problem, there are infinite ways to assign integral values of a complete graph. Our solution is that by restricting to only looking at configurations within the period and fixing a single vertex at 0 chips, that's our way of dealing with this k-scaling business. If I choose one of my vertices, I give it a name, I call it V0, and I give it 0 chips, and I say every configuration I'm interested in has U at 0 chips. That gets rid of this k-scaling of adding a constant k to every vertex. Because since this one's stuck at 0, that's just never going to apply. By applying these configurations, by applying these restrictions, we avoid the problems of infinite prepositions outside the period and infinite ways to add a constant to each vertex. We now have a finite number of configurations to count. Okay, I'm going to go back to here. The number of configurations of a complete graph that exist inside the period. We're going to use previous results on board pile polyominoes. And I'm going to get to that in a second. So again, I'm trying to tell the narrative of how I started with a problem that didn't make sense, how I've now turned it into a problem that does make sense, into now we're actually going to try to find the solution to it. Well, your first tool that you often come up with is brute force. So I just started writing down all of the period configurations that exist. So let's look at P2 or K2. So it's very simple. There's only two vertices here, and there's an edge between them. How many different ways can I assign chips to these vertices such that we are already inside the period? And now I'm going to see if I can write in real time on this. Okay, let's try this. So I have 0, 0, and 0, 1 written here as my period configurations. Remember that my rules state that I need to fix one of my vertices at 0. So I'm going to fix one vertex at 0. And I'm going to ask myself, is there any other integer that I can assign to this second vertex such that, is there any value I can assign to this vertex such that we're already inside the period? Think about if I assigned the value 2. Well, diffusion dictates that the next step is going to take me to 1, 1, because the 2 will fire to its only neighbor, and we're down to 1, 1. Well, after 1, 1, it's just going to repeat itself forever and ever. It's 1, 1. That means 0, 2 wasn't in the period, because the period only has one configuration in it, 1, 1. Let's think about another example. What about 0, 3? This is going to go to 1, 2. And then that will turn into 2, 1. Now this 1, 2 and 2, 1, that's the period. That's just going to bounce back and forth forever. So again, the 0, 3 was not inside the period. Now, what is interesting is I could use 0 and negative 1. And I'm going to start erasing some of this stuff to give me some room. If I write 0 and negative 1, well, that's going to become negative 1, 0. And then they'll just go back and forth. So the configurations that I had written down already coming into the talk are just the ones that deal in non-negative numbers. But you can see how if I added in the negatives, I would add a few additional ones. So we have our K1s. Now K1's extremely boring because there's no edges in it. It's just one vertex. We have our K2s, which depending on how you look at it, there are 2 or 3 ways to do it. Get a little more interesting when you look at the K3s. Remember, K3 is the complete graph on 3 vertices. So that means every edge exists. So there are actually 6 examples here, even more if you look into the negative ones. And this is just me 4 years ago writing down everything that I could and trying to generate a sequence of numbers. So this is the sequence that I managed to generate by hand. 1, 2, 6, 19, 61, 196, 629, 2017. And Sometimes that does you some good, sometimes it's completely useless. But what it does do is it gives you access to a tool that, if you're going to be a graduate student in math, I am sure at some point you will find useful. And that is the Online Encyclopedia of Integer Sequences. So this is exactly what I did when I was a master's student or a PhD student. I just typed in my sequence. 1, 2, 6, and of course my history remembers it because this is not the first time I've done it. And what the OAIS would give me is the list of every sequence in the world known to man. So let's actually get a little simpler. Let's just go 1, 2, 6, 19 first off. There are 150 results. That means there are 150 recorded instances in mathematics of different sequences that at some point have the numbers 1, 2, 6, and 19 in some order. So what would happen is I would generate a new number. So say it was the first time I calculated 19. Well, now instead of searching 126 into the OEIS, I was searching for 12619. And I got, there's still 150 results. So then I had to plug in another number. I calculated 61 by hand. It was no fun, but I did it. I now have 15 results. I could go through these 15 results and try to figure out if any of them make any sense to perhaps be the thing that I'm calculating. Or I could calculate another number, 196. Throw that on the pile. Down to 2 results. It's either the number of board pile polyominoes with n cells, or it's the number of d plus d minus diagonally convex polyominoes with n cells. It certainly seems like I'm dealing with polyominoes. So then I finally added in my last term 629. I got that if this sequence is something that has ever mattered to anyone in the past, then it has to be about board pile polyominoes with n cells. That was completely Greek to me when I first read it. And every time I plugged in another number, I was hoping it would be something more sensible. But no, as more things were shooing away, all that remained was the number of board pile polyominoes on n cells. So I figured that's what I got to do. I got to start searching for papers on what is a polyomino, what is a board pile polyomino, what even is a cell. That's the point I was at here. So I did the work. I found some papers, and the OEIS is great because it will actually give you a number of papers. Oh goodness, look at this. This is new. That's me. There we go. So somehow the OEIS has already picked up that I used this sequence because I didn't send this in or anything. That's cool. I actually was reading David Klarner's paper, Some Results Concerning Polyominoes, when I was doing it. So now we're going to actually talk about what a board pile polyomino is. A couple of things that most of us should be familiar with. We know what dominoes are. And a domino is a rectangle that's broken into 2 squares. So there's 2 ways that you can orient a domino. You can either have it sideways or straight up and down. I suppose you could have it kind of at an angle, whatever, but we're going to just look at these 2. Now, a polyomino just means there can be more squares than just the 2 in a domino. So it could go up to the tetraominoes, which we would know as our Tetris pieces. So in Tetris, I think there's commonly known as only like 6 or 7 pieces, but we look at all the flips and rotations and stuff. So there's 19 tetraominoes. And here they all are listed for us. So what this seems to be telling me is that my question on period configurations of the complete graph in diffusion is somehow related to the number of these polyominoes that exist, which is, it was very surprising, and I thought it was kind of neat. So it gave me something to work with, that's for sure. So it didn't just say polyominoes, it said board pile polyominoes. So I had to look up what that meant. And that means, well, polyominoes look like a pile of boards, but we can do better than that. So there can only be one strip of polyominoes per y coordinate, is the way I usually think of it. So my first example here, every if you want to look at these as y coordinates, only has one connected row of cells. Whereas this example on the right, well, the bottom actually has 3 different connected rows of cells, and the next y coordinate up has 2 different connected y coordinates, 2 different strings of cells. So we've got an x next to this. This is not a board pile polyomino. It's not what we're counting. On the left, it's things like this that we're interested in, board pile polyominoes. Only one board per y coordinate, as I said. So I hadn't solved my problem yet, though. I had found something that seemed to be something similar to what I was measuring. The numbers coming up were the same, but you can't really write that down in a paper until you've proven that it is actually a one-to-one mapping, an isomorphism in this case. So now we must find an isomorphism connecting complete graph configurations in diffusion to these board pile polyominoes. So this is the part in the talk where I usually like to just give everybody a second to think about this. This is, again, taking a step into my world, me in my office at Dalhousie, just writing down, okay, I'm going to look at a very simple example, but hopefully not trivially small. And I'm going to try to figure out how these things map to each other. So I'm going to give you a couple minutes just to give you a brief exercise. And I want to ask you the same question that I had to ask myself. Is there some way that I can map these strings of digits, which represent the 3 stack sizes on triangles that exist inside the period, to the number of board pile polyominoes that exist on 3 cells? And of course, I could just draw lines wherever I wanted and say, there, that's my mapping. But if it doesn't extend to larger sizes of n, if it doesn't extend to the tetraominoes or the pentominoes, then I didn't accomplish anything, I haven't proven anything. Is there a sensible way, a way that follows some sort of pattern that I can map these? That's the question that I had to ask myself. And just to not steal your fun, just in case there's anybody out there who wants to take a minute and think about this, I'm going to give you a minute or two and just see if you can piece this together. What kind of sensible mapping can be made that could possibly be extended to larger sizes? Uh-oh. I'll get you back.
If we want to follow anything in chat, I know that Robert, our vice president internal, made a comment about how the dominoes remind him of. Oh, you can see me on there. You don't need to switch back. You can go back to the whiteboard.
Oh yeah,
sorry about that.
Screen.
They remind him of the Young's tabloids and the Sprecht module for symmetric group of order n. Does that mean anything to you?
Okay. Here's what I can offer, because group theory isn't really my thing, but somebody did raise their hand during one of my talks and say that these complete graph configurations do map to an abelian group. And it's based on the, let me remember this properly, I believe it's the mod n number of chips in the configuration. So if you think of 0, 0, 0, that total is 0 mod n. 0, 0, 1 has 1 and 0, 0, 2 has 2. 0, 1, 1 exists in the same group as 0, 0, 2 because the sum is the same mod n, mod 3. And 0, 2, 2 exists with 0, 0, 1 because 4 mod 3 is equal to 1 mod 3. And what this means is it was amazing. When he raised his hand, he had already defined some sort of addition between these that perhaps I could try to go over with you. But he was adding the least stack size and then the second least stack size and then the third least stack size to each other. And that was the operation within this abelian group. Yeah, so that's what I can offer. There is some abelian group relationship going on.
Okay, and then we just got a recognition of a typo that I said because I read Robert's message. It's a tableau. I think that's maybe the correct way to pronounce that. Okay, I'll let you resume. Hopefully, everyone's
Okay.
discerned
Yeah.
this pattern here.
So I'm not going to ask anyone to raise their hand or offer their opinion. You can all just smugly smile at your computer and say, I got that. So I'll now give you the solution. So there are a few solutions to this, but my idea was, let's just say that the things on the bottom should be zeros, because that makes sense to me that if you're the least, you should be 0. Then I ran into this problem of 0, 0, 1, 0, 0, 2. I didn't know where to put the 1, where to put the 2. So the way I arranged it is I said that if the second level of squares is as far left as possible, like this one is, then I will only increase by 1. Whereas if it is a little bit further right, I'll have to increase by 2. And in larger examples where it's even further right, I'll increase by 3. So I get my 0, 0, 1 that way, my 0, 0, 2. That same pattern can work with 0, 1, 1 and 0, 2, 2. And then nicely, my 0, 1, 2 works the same way because everything that's on top is bigger than the thing below it. And if you do have the possibility of moving right or left, you just have the rightmost possibility being an addition of 1. But you could have come up with the same example where you had the zeros on top and you moved from right to left instead of left to right. And due to, reflections and whatnot, it's the same thing. So I guess there's like 4 different ways this could be done properly. So now the question is, what does firing look like? Because again, I haven't proven anything. I haven't shown that this actually does work for every size n. I've just found a mapping that seems to make some sense to me. So let's think about what firing looks like. My configuration 6643330. Now, if we think of that as a graph, think of it not as a polyomino. That is K7, the complete graph on 7 vertices, where 2 of the vertices have 6 chips, 1 has 4, 3 of them have 3, and 1 of them has 0. If that thing were to fire, well, the 6s both have 5 poorer neighbors, so they're going to go down to 1s. 4 has 2 richer neighbors, so they go up to 6, but then 4 poorer neighbors, so they go down to 2. The 3s have 3 richer, 1 poorer, so they go up to 5, and the 0 has 6 richer, so it goes up to 6. So I've created this 1, 1, 2, 5, 5, 5, 6. But there's quite clearly a problem, because it doesn't follow my rules anymore. I've now got the smallest ones up top and the biggest ones on the bottom. Something has happened. I'm going to reorient these following my rules. Now get my 1s where they belong, the 2 is above it, the 5's above that, and the 6 above that. And what should be recognized here is that this is a reflection along the x-axis. So this is an amazing little thing to stumble on, because I started with a problem before I ever knew about these polyominoes. I was dealing with complete graph configurations, and I proved, well, I didn't prove, somebody else proved, that the period could only be length 1 or 2. So when I stumble into this polyomino business, and I start asking, how am I going to prove that this is period 1 or 2? Well, now I've shown, and again, this is one example, I'll spare you the entire proof, that every time you fire, you actually flip along the x-axis. And what we know about flipping along the x-axis is if something is its own mirror image, that will be our period 1 case. If something is not its own mirror image, well, that's going to be period 2. Because think what happens if I do an x flip along this bottom thing. Well, it goes back to where I started. So, and again, to finish this proof, let's take this thing and fire it a second time. If I did everything right, it should be where we began. Well, the 6 fires down to 0, the 5's down to 3, the 2 goes up to 4, and the 1's go up to 6. And this thing is actually equal to what I started with once I reorient properly. Because again, the 0 is on top. The 0 doesn't belong on top. I defined it as being on the bottom. So once I flip it properly to follow my rules, I've shown that these things always have period 1 or 2. So that's like I find to be such a super neat result that I stumbled onto, because before, I never had a thought about X flips until I started firing these things and seeing what happened. And I had never really even given thought to the fact that whatever pattern I see here, it better only show period 1 or 2. And lo and behold, it did. So, in fact, firing always causes a flip along the x-axis. Without performing any calculations, we know that a firing will make polynomial A to polynomial B. So I've drawn these here. Polynomial A, such a very ugly and complicated polyomino. I may have been saying polynomial. I fall into that sometimes. Polyomino. Polyomino A, its x flip is B. I don't need to plug in all the proper numbers and do the calculations. I know that if there is a complete graph that maps to this A, well, all I got to do is flip the thing along the x-axis, and that's what it will fire to. This thing has period 2. An example of period 1 is something like this, where everything starts with 0. Well, if they all fire, the x flip of this flat rod is just itself. This is an example of period 1. Not every x flip gives you a different shape. Some of them are their own mirror image. I have a little bit of time left, so I'm going to rush through paths and try to explain that. But this is really the end of complete graphs. I started with a question that didn't make any sense. I had to first refine the question to make it make sense. I had to then do a million tedious calculations until I had enough for the OEIS to help me. And the OEIS will not always save you. As you'll see with paths, it did not save me. But it did here. It gave me something, but it didn't give me the proof. So I had to then start to play around with the sequence that the OEIS gave me, and again stumble onto another relationship, this X-flip business that really helped me to prove the relationship. So hopefully this is what happens when things go right in grad school. Paths should be a warning sign for when things go bad. So I wanted to do the exact same work on paths. I wanted to figure out, up to isomorphism, forgetting pre-periods and forgetting k-scaling, how many different configurations exist inside the period. So I started with the brute force. I did some calculations. I got my sequence of numbers, 2, 8, 26, 96, 346, 1248. Let's go to the OEIS. 2, 8, I've already forgotten it. 26, 96, 346. OEIS has never heard of it. So I ran out of ideas. I didn't know what to do now. I didn't have my fallback option to save me. So the problem on paths is it's not analogous to some other well-known problem. We must first look at the underlying mixed graph. So what became of use with paths is looking at the mixed graph that represents how the chips flow. So a mixed graph is a graph where the edges aren't just edges. Some of them may be directed to the right or directed to the left, and some of them might be what I call flat, which means undirected. So if we look at this first graph here, the chips flow along these directions. 1 goes to 0, 1 goes to 0, 1 goes to 0, and 4 goes to 0. So I'll skip past admissible and period. What I wanted to get to is to figure out, for these underlying mixed graphs, can they all exist for paths? Or are some of them just not possible to exist inside the period? What I got is this rather ugly list of sub-orientations or subgraphs that can't exist. Like, I found out that you can't have two flat edges next to each other. If you do, you can't possibly be in the period. Or I'm going to let these squares represent endpoints. So if you have a left or a right facing edge next to a flat, next to an endpoint, that doesn't work. And things are just getting more and more complicated. Number 4 is I can't have a right edge next to a flat edge next to a right edge. The 5th one was the worst one. I went for weeks and weeks, maybe months, thinking that the top 4 were the only 4 that existed until I stumbled on number 5. Right cannot exist except when it lives within the subgraph left, right, left. So this problem, I haven't even gotten to counting the configurations yet, and I'm already into 5 different cases territory. So I got to figure out what to do from here. I'm still looking for all the underlying orientations because I think that if I can break this problem into smaller pieces, say if I'm trying to count to 1,000,000, well, it might be quicker to say there's 1,000 suborientations, and for each of those 1,000 suborientations, there's 1,000 configurations, rather than just trying to count from 1 to 1,000,000. So I'm trying to break the problem into smaller pieces. I know the periods can only be of length 1 or 2. So why is it that right, flat, right can't exist inside the period? Like, what goes wrong if I'm trying to assert that that's true? Here's where I'm going to do a quick little proof of that. Suppose that I'm inside the period, and that means that 2 steps from now, I have to repeat, because the period is only length 1 or 2. If it doesn't repeat, that means that this was a pre-period position all along. If I'm supposing that I'm inside the period, let's give these integer values. Let's say there's k on these two, because they're equal. This k has to be richer than its neighbor on the right, k minus j. So it must be some integer smaller. This k plus l over here, since it's richer than k, it gives a chip to k. It has to be richer than k. So k plus l, we'll say. So let's see what happens when this thing fires. K plus L fires to its poorer neighbor K, so it becomes K plus L minus 1. And K has received a chip. It's now K plus 1. This thing's flat. Nothing goes along this flat edge. And then the last thing is this K here is going to give to K minus J. So it goes to K minus 1 and K minus J plus 1. The problem is, I know that in order for my K plus L minus 1 to get back to K plus L, well, it's going to have to receive a chip. And I know that for my K minus J plus 1 to get back to K minus J, it's going to have to lose a chip. And when I follow that argument, I now have K minus 1 and K plus 1 along what is supposed to be a flat edge, but it's quite clearly not, because K plus 1 is richer than K minus 1. So that's my contradiction. I just ran through 2 steps, and I got that it couldn't possibly be in the period, because I did not get back to my starting position with a couple of K's in the middle. I got a K minus 1 and a K plus 1. And that's the type of proof that I had to do for each of these little cases. So I now have a rough idea of what the underlying mixed graphs can look like, or mostly I know what they can't look like, so they look like everything other than that. So I had to ask the question, given a mixed graph, how many different period configurations can induce it? For example, if I was given the orientation or the mixed graph right edge, left edge, right edge, well, that is satisfied by assigning 1, 0, 2, and 0. And that is actually inside the period. You'll see that it goes down, and then it comes back to itself. So that is one period configuration that satisfies right, left, right. But there's another one. I could go 2, 1, 2, 0. It has the same underlying mixed graph, and it is inside the period. So there's at least 2. My question is, for every one of these underlying mixed graphs, how many configurations work with that? And then I'll just add them up. So we begin by assigning the leftmost edge to have 0 chips. Remember, those previous rules from before, they have to still be in effect. So I can't allow for this k-scaling business of just adding 1 or 2 to every stack size. So I have to choose one vertex from the get-go to have 0 chips. That's my B naught here. Well, the question I have to ask is, how many different stack sizes could V1 have? Because remember, my goal is to count up all of the configurations that could be implied by this underlying mixed graph. So I have some stack size here that is richer than 0 because it's giving to 0 in the first time step. So that's my first inequality. Stack size of V1, I use absolute values for stack size. The stack size of V1 has to be greater than V0. And I know that the stack size of V0 is equal to 0. But I have a little bit more information. Since we are inside the period, V0 will have to return that chip in the next fire. Think about it. If V0 receives a chip initially, it's going to go up to 1. That 1 needs to go back to 0, or else I was never in the period to begin with. So it will have to give it back to V1. In order for it to give it back to V1, at that time, V1 would have to be poor enough. So I get a second inequality. The stack size of V1 minus 2, that is, minus the things it loses in the first firing, must be less than the stack size of V0 plus the one chip it received, in order for V0 to be richer in the second step, so it can give to V1. So the only option for the stack size of V1 are 1 and 2. That's because, if we look back, we need values for V1 that are greater than 0, but they have to also satisfy my V1 minus 2 is less than V0 plus 1. The only two values that satisfy that are 1 and 2. So I get that there are two possible values, 1 and 2. Similar calculations can be done to show that there are 3 options for V2 and 2 options for V3. So what I've actually done is I've shown that there are 2 times 3 times 2 configurations which both exist inside the period and induce my underlying mixed graph left, right, left. Now all I need to do is iterate that calculation over all of the different underlying mixed graphs, which is going to take a long time. So what I need to do is assign a multiplier to every vertex depending on its neighborhood. In the same way that I looked at this vertex right here and I said, well, if I know that there are 0 chips on the vertex next to you, how many stack sizes can you take on? And I know there are only 2 possibilities, 1 and 2. Well, I need to be able to do that for any vertex in any subgraph of the path. So that is what we should have here. This table shows for every possible underlying mixed graph, if I'm interested in finding the multiplier of the black vertex, it's either 3 if it comes in any of these cases, 2 if it comes in any of the cases here, or 1 if it comes in any of these cases at the bottom. And if this looks like an awful mess that is not nearly as clean as the complete graphs, that's because it is, and it should look that way. This was not a clean calculation. This was brute force, absolutely. What we were able to get from this, we weren't able to get a beautiful proof like what we found on the OEIS, that we have a nice sequence that is already referenced in previously published papers. What we were able to get was at least a recurrence relation, which says that Tn, the thing I'm interested in, the number of configurations that exist on a path with a certain number of vertices, well, it's equal to 3 times the previous value, plus 2 times the value before that, plus the value before that, minus the value before that. And if you have any experience working with recurrence relations, you'll know that this is awful, because you're used to only working with things maybe of 2, a degree 2, possibly up to 3. But when you get up to 4, there's a proof that up to 4 or 5, you're not even guaranteed to find roots, things like that. Like, this is just awful. And when you actually conduct the calculations, you find these infinite decimals, these irrational numbers. There are no nice roots here. There's no nice answers. This is as good as this is going to get, sadly. And sometimes in grad school, that's what you need to accept. And that's a very down note for me to end on, but that is what I'm going to do. So thank you. Okay. So my experience has been, like I say, in dynamic processes on graphs, chasing robbers around a graph, or maybe a firefighter trying to put out a fire. Really neat stuff, I find. But when I got here, you know, you're always diversifying your mathematics portfolio. So I'm doing graph coloring now, which maybe speaks to a few more people, and maybe in a few months' time, I'll be prepared to give a talk on that. But now what I know is dynamic processes on graphs. So that's what I've been speaking about.
Nice. Okay, I just realized that I was muted the whole time because I mute myself on the other program, but I was applauding. I was saying thank you, Todd, and I was asking for any questions from people in the chat. Sorry about that. I always mess things up somehow or another, but uh, now that my audio is on, I can thank you in front of everyone rather than just between you and I. Um, but if there is no more questions, I think it's been a minute or two. I'll applaud again as is customary as well. But yeah, thank you again. And this is going to be the end of us for this semester. I don't think we have any more events involved. There's a colloquium talk in the department on Friday. If you're interested in that, we sent an email about that as well. But yeah, thank you for attending and thank you for speaking to us, Todd.